You know that feeling when your phone just freezes? It's annoying, for sure. But what if that same kind of software bug happened in, say, a self-driving car or the power grid? All of a sudden, it's not just an inconvenience anymore. It's a potential disaster. We live in a world that is literally built on code. So the question is, how can we be absolutely certain that that code is perfect? I don't mean just well-tested, but mathematically, provably correct.
So yeah, that's the big one, right? That's the question we're diving in today. When a system is absolutely critical, how do you get past, well, it seems to work okay, and get to a place of absolute, rock-solid certainty? Is it even possible to prove with 100% confidence that a piece of software is completely flawless?
Well, believe it or not, it is possible. And the answer comes from this really fascinating field that sits right at the intersection of pure math and computer science. It's called formal verification. And it's all about using the pure power of mathematical logic to prove that a system does exactly what you designed it to do. No ifs, ands, or buts, no exceptions.
So in this explainer, we're going to go on a bit of a journey, following the core ideas from a really foundational paper on this whole topic. We'll kick things off by understanding just how big this challenge is. Then we'll see how the fundamental building blocks of math itself, we're talking set theory, give us a foundation to build on. We'll check out two really powerful tools for defining things with perfect precision, see them in action, and then at the end, we'll see why this all leads to a whole new level of trust in our technology.
All right, let's start with the stakes because they are high. I mean, think about the code running in a pacemaker or an airplane's flight control system or a nuclear power plant. In systems like these, a bug isn't just an oopsie, it can be a life or death situation. Now, your standard testing can catch a lot of errors, that's true, but it can never ever prove that there are no errors left. For that, you need a completely different, much higher standard of proof.
So the approach in the paper we're looking at is to build these proofs on the most fundamental language in all of mathematics, set theory. To be specific, a system called Zermelo-Fraenkel set theory, or just ZF for short. And it does all this inside a really powerful piece of software called the Isabelle theorem prover. You can think of Isabelle as a kind of high-tech workbench for mathematicians, designed to help them build and double-check these unbelievably complex proofs.
And listen, ZF set theory isn't just another page in a math textbook. This stuff is the bedrock. It's this small, elegant set of rules that are so fundamental, you can use them to construct everything else in math. Numbers, functions, you name it. It's kind of like the ultimate source code for logic itself.
So the real goal here isn't just to scribble some math on a whiteboard, it's to mechanize it. The mission of this paper was to build a toolkit that takes these incredibly deep, powerful ideas from set theory and turns them into actual, practical, automated tools that engineers can use to build systems they can truly mathematically trust.
So how do we even begin to build that trust? Well, our first tool from the kit is all about making perfect, unambiguous definitions. I mean, think about it. If you want to prove something is correct, you first have to define what it is with absolute precision. And this is where a really cool concept called inductive definitions comes into play, built on an idea called a fixed point.
The key idea here is the least fixed point. And honestly, that recipe analogy is the perfect way to get it. Imagine you have a recipe. The least fixed point is the final dish. It contains only the ingredients and follows only the steps from that recipe. There's nothing extra thrown in and nothing is left out. It is the most precise, minimal, and correct result you can possibly get. Okay, let's make this real. How would you formally define something as basic as the natural numbers? 0, 1, 2, 3, and so on. Well, using this method, you'd start with a base case, a set that just has 0 in it. Then you add one simple rule. If any number x is in our set, its successor, the next number, has to be in the set too. So what's the least fixed point of that rule? It's the absolute smallest set that makes that rule true, which is, perfectly and elegantly, the set of all natural numbers.
And this isn't just some clever little logic trick. This whole method is guaranteed to work because of a heavyweight champion of mathematics called the Naster-Tarski theorem. This theorem is the formal, rock-solid guarantee that for a huge class of rules like the one we just saw, a least fixed point not only exists, but it's unique. It's the mathematical engine that makes this whole thing run.
Okay, tool number 2. This one tackles one of the most classic and dangerous bugs in all of programming, the infinite loop. Right? We've all been there. To have a provably correct program, we absolutely need our functions to be mathematically guaranteed to finish their job. We need to make sure our recursion always ends. And the concept that gives us this incredible guarantee is called a well-founded relation. The staircase analogy here is just perfect. A well-founded relation is like a staircase that you know for a fact has a bottom floor. You can always take a step down to a smaller element, but you can never, ever step down forever. Sooner or later, you're guaranteed to hit the ground.
Now, you've probably run into simple structural recursion before. It's like processing a list by always looking at the first item and then the rest of the list. Kind of like peeling an onion, one layer at a time. But well-founded recursion, that's way more powerful and general. It lets you write complex algorithms, like quicksort, where the program calls itself on smaller pieces of the problem, but not necessarily in that simple, predictable, one layer at a time way.
So here's the bottom line. By defining our recursive functions using one of these well-founded relations, we get the ultimate safety net. We aren't just crossing our fingers and hoping the function stops. We have a formal mathematical proof that it will never get stuck in an infinite loop. It is guaranteed to finish. Period. Okay, so we've got our tools. One for making perfect definitions, and one for making functions that are guaranteed to finish. Now for the really cool part. Let's see them in action in the ultimate test case. The paper uses this very toolkit to do something pretty mind-bending, to prove that an entire system of logic is itself sound. This is the system of logic they're looking at. You've got three axioms, K, S, and Dn, which are basically the fundamental unshakable truths of this little universe, and then you have one rule for how to create new truths from old ones, called modus ponens. Together, this is a complete, tiny system for basic logical reasoning. And here it is. This is where it all clicks together so beautifully. The set of every single theorem that can possibly be proven using these rules is defined as, you guessed it, the least fixed point of those rules. We are using our first tool to perfectly define the entire possible output of a logical system. It's an absolutely perfect demonstration of these ideas working together. So let's zoom out for a second and look at the big picture. What does all of this really mean? Well, by mechanizing these deep mathematical concepts, this paper did way more than just prove a few theorems. It actually built a reusable, rigorous foundation for creating computing systems that we can actually genuinely trust. So let's just quickly recap the main takeaways here. This work took these abstract, super powerful concepts like least fixed points and well-founded recursion and actually forged them into a concrete, working toolkit inside the Isabelle software. And by doing that, it provided a solid foundation that other engineers and researchers can stand on to formally verify their own complex critical systems.
Because at the end of the day, formalizing mathematics like this isn't just some dusty academic exercise. It's about forging a whole new class of engineering tools. These are tools that let us build a safer, more predictable, and more reliable world. One that's built not just on hoping for the best, but on a bedrock of pure mathematical certainty.
And that kind of leaves us with one final question to think about. As our lives depend more and more on incredibly complex code, from our finances to our healthcare to our transportation, what is the one critical system out there that you would want to know without a single shadow of a doubt is 100% formally verified?